Much for joining us for our Lunch and Learn on geology of the Maine Coast. Our speaker today, Dr. Joe Kelley, is a professor of marine geology at the University of Maine. In today's presentation, he'll share a crash course in the three elements of the coast: bedrock, glacial deposits, and modern processes, and explore the impact of sea level on evolution of the modern coastal landscape. Next slide. My name is Kathleen Neal. I'm the Director of Policy and Partnerships at Maine Conservation Voters and Maine Conservation Alliance. Our organizations work to protect Maine's environment and our democracy by building diverse coalitions, influencing public policy, holding politicians accountable, and winning elections. Next slide. A few technical notes for today's event. You are all muted, but we do want to hear from you. Please send your questions to me, Kathleen, through the chat as they occur to you. You can find the chat by hovering your mouse over the bottom of your screen, and I'll keep track of the questions to ask Dr. Kelley during the Q&A session at the end. If you're having technical difficulties, please message Will Sedlak, also through the chat function, and he can help you out. This event is being recorded, and the video will be posted on our website later this afternoon, along with recordings of all of our previous Lunch and Learns. Thank you again for joining us, and Joe, I will turn it over to you.
Okay, that's often a dangerous thing to do, but I'm seeing my PowerPoint. And I think we're there. Thank you. So I'm going to talk about the Maine Coast. I teach a course, and for 14 weeks, 3 hours a week, I lecture on this. And now it's going to be 30 minutes. So it is quite condensed. I've often thought to myself, I could, I'm not advancing. Okay. That I could give an entire lecture on this slide, because it really has all of the things in it that that the Maine Coast possesses. If you can see the text up there next to, this is a sand beach in Acadia National Park. You can see the text says bedrock near the bubble, and much of what you see in the field of view is bedrock. It's granite, and it was the liquid molten rock beneath huge volcanoes a long time ago. But bedrock is the framework of our coast. It's the skeleton. Everything else is arrayed on it, and it is the dominant feature of our landscape, even though sometimes you don't see it. Ice Age materials, the superficial geology, ranks beneath that, and much more recent, only about 15,000 years old, unlike 400 million year old granites. The parking lot you can see just beyond my text there is built on a terrace-like feature. There's one on that side, there's another on the other side of this little river valley. And they were deposited by glaciers about 15,000 years ago, when actually this landscape was underwater, but with large glaciers melting away on the mountaintops. And finally, there are modern processes and sediment, where modern things are sculpting this coastline, and they're working with glacial materials, they're working with bedrock. If you notice the bedrock on the beehive there, at the back, you notice a big kind of shadowed area that's an embayment. That was a major landslide. I mean, a really large landslide that would probably make national news if it happened today. We don't know when it happened. There are ways to determine that, but it was probably a long time ago and is not likely to recur there. But then again, we don't know, but that would be a modern process. So just looking back at the overall region we're in, there's the state of Maine, there's our coast, there's our offshore area. Pretty much everything you see is bedrock. Sure, there's some mud at the bottom of some of the deep basins in the Gulf of Maine, but really that's a bedrock coastline, and you can see how varied it is. It's our skeleton, and because it varies from place to place, our coast changes from place to place. The rocks were added in a complicated series of collisions between continents and microcontinents, the continents being Europe and North Africa, microcontinents having unusual names, but think of places like the Japanese archipelago or Indonesia smacking into North America. and giving us very different rocks. They're near each other today, but they never were in the past. They have different fossils, different everything. They're quite different from one another. I think the first paper I wrote when I came to Maine was just looking at the coast and talking about it. And you can see I named it several cutesy sort of names to talk about it, the way it looks. Each of these is a completely distinct bedrock terrain. And in fact, in Penobscot Bay, there's more than one completely distinct kind of bedrock. The white text you see there is the tidal range, which also is an important process and increases rapidly as we move up toward the Bay of Fundy. I'll make a slight note here, 400 kilometers as the crow flies, but 5,600 kilometers along our tidal shoreline. But even that's not fair. If you see that little inset map with the red hatched areas, we only consider our tidal shoreline areas with cove openings larger than 100 feet. If it's smaller than 100 feet, it's not part of the coast. So you can see the red areas don't get counted, but if you counted all of the areas of the Maine coast, it would be significantly longer. The reason that's important is that we get federal monies as a function of how many people live on the coast and how long it is. And it's actually treated as a much shorter coastline than it actually is. So I'll just look at each of these compartments briefly. The Arcuate embayments, you can see on the map on the left, those checked areas, the blue, the kind of pale areas, are granites, and they resist erosion. And you can see this little cove here, Horseshoe Cove, with granite islands or peninsulas. The metamorphic rocks, the altered materials in between, are all eroded low and covered with modern materials. So in this coast, we see it dominated by sand beaches, protecting salt marshes, with granite headlands very common. Moving up toward Portland, after Portland, we get into the indented shoreline, very different geometry to the coast. Here, the rocks trend northeast, southwest. And then as you move up toward the Kennebec River, there's an abrupt change because of faulting, and they trend more north and north and south, offshore, onshore. And as a consequence of that, they're very different coastal environments. The protected areas where the rocks trend north-south have vast mud flats and are very protected, a lot of marshes. The other areas that are more exposed are going to be much rockier. No marsh could survive in Cape Elizabeth, in those places, too much wave energy. So the orientation of the rocks provides shelter, which indeed determines the nature of the coastline that will exist. I can't get into the rocks here deeply other than to show you two that have been mapped as very similar to one another in terms of when they formed and where they formed, but they look very different. The Boothbay Harbor rocks in the upper left were heated much, much more. All of these rocks have been down under the ground several miles, but there they were heated up even a bit more. The quartz and the feldspar, the light colors, have begun to melt and become plastic, and they're wrinkling under pressure. Whereas over in Two Lights State Park, they have not done that. They have been not subject to nearly the same temperatures and pressures. Even though they began in the same place, they weren't buried as deeply and look very different. When I worked for the Maine Geological Survey, we used to get fossil petrified wood brought in all the time from Two Lights. It's not petrified wood, I promise. Moving up the coast to the Island Bay areas, you can see on the map, all that blue is granites. And they're all about the same age, about 400 million years old, 450. And they were the molten bodies of rock that fed enormous volcanoes, indeed super volcanoes. If you notice the little green hatched area near Katahdin and near the Cranberry Islands, that's all we see of the volcanoes today, of the volcanic rocks. Again, these granites formed 5 to 7 miles beneath the Earth's surface. So we've had a lot of erosion in 400 million years. But by measuring these volcanic deposits, Sheila Siemens from UMass came out with this illustration in a paper recently that suggested these were all some of the largest volcanoes that erupted in Earth history that we know about. Not just big, we're talking super large. The Katahdin and Traveler Rhyolite were just vast, vast volcanic eruptions, so much so that New York State has a number of sedimentary rocks that are volcanic ash deposits from this region. Finally, the cliff shoreline, you can see the faults on the map to the lower right, separating our coast from what you would see underwater, very deep underwater, are very easily eroded sandstones from the Bay of Fundy, but those are not visible because they've been eroded deeply. On the left, you see the Cobscook Bay area, which is a fold. If you took a piece of paper and folded it and then plunged it into the ground, you'd see what you get here: peninsulas of resistant to erosion rocks and embayments with rocks that have already eroded out. That's just a picture on the upper left of the Oak Bay Fault. You don't see it. I was actually hired to work in Maine to begin looking for signs of its activity. It is not active since the last ice age. I can't really see, again, the fault along the outer cliff coast, but you can see the bedrock cliffs and the gravel beaches that really dominate that region. Toward the end of the formation of the rocks, many continents had come together. Europe and North Africa were joined with us, insulated a lot of heat from the earth from below, and led to melting. And we had volcanic rocks beginning to erupt again. You can see the black arrows pointing to black rocks, and you can see one of them close up on the lower right. These are basalt, the rock of the ocean basins, the rock of the dark areas on the moon. And these were the pipes. They weren't really pipes, they were more tabular, but they erupted, not in volcanoes. This was so hot, it was really liquid rock, poured like water over the Earth's surface, hundreds and hundreds of meters thick, really baked our area, but that's all eroded today. We just see the remnants in terms of these black volcanic dike rocks. But they mark the beginning of the formation of the Atlantic Ocean. There are some benefits from these rocks, economic deposits, the Deer Isle granite, and many other places we find granites used for a number of purposes. We only have one real big limestone deposit. It's actually a marble. It's been metamorphosed, but it's in Rockland, and you can see, if you drive on Route 1, it's a narrow distance to the fall on either side, but very valuable deposit. I put this in, I don't know if my friend Beth Ahern is looking, but this is the Harborside mine in the Katahdin area. And it's the last metal mine that existed in Maine. The photos were from my friend Fred Beck, who was the site geologist. And you can see this was more than 100 meters deep, more than a football field deep. They extracted copper and zinc and probably gold. But it played out, and they opened it up to the ocean again. It was a small embayment before. And for a time, that was one of the largest waterfalls, probably the largest waterfall in Maine, and one of the largest on the East Coast. It would probably make national news if somebody did something like that today. But this was a disastrous area. The mine was just left the way it is. There was it's a Superfund site today, unfortunately. So just a cross section, the rocks, there's not a lot. It's all old stuff. There's not much material on top until you get to the Bay of Fundy, rather to George's Bank. And there you can see on that upper cartoon to the left how thick that is, 16, 20,000 feet of sand and gravel and mud. Glaciers, a mere 15,000 years ago, probably earlier than that, but the first dates we have are from 15,000 years ago, and Mount Desert Island might have looked at like the image on the left, though it is Glacier Bay. And the glaciers caused both erosion, giving us deep areas like Somme Sound and many of our lake basins, and they formed deposits. There's two deposits seen on the right, really critical because they were the first ones really recognized. What you see is a glacial deposit on the bottom, and then the ice pulled back and the ocean flooded the area and fossils came in, shellfish and seaweed. And then the ice advanced again, preserving that ocean record. We can radiocarbon date these. This is an old illustration on the upper left. We think these were about 15,000 years ago today, but that graph also shows what happened as the ice begins to melt. Its vast weight is taken off the Earth's surface and the land moves back up again until you get to the present with Mount Desert Island, Acadia National Park shown as the funny little bump there. But the Earth's crust was depressed significantly at the time of the Ice Age. This just shows some glacial deposits, one forming in Glacier Bay. This is Muir Glacier. And you can see the ice in the background and the ridge of debris it's left. It's called a moraine. The ice re-advances again in the winter, deposits more material, and can form a sizable hill of sand and gravel and mud. You can see an older one, much older, about 15,000 years old, at the entrance to Machias Bay on the lower right. all of our bays were at one time or another blocked by glacial moraines like these, giving us the many lakes that had existed but are no longer present in those areas. Second major feature is there are ice tunnels as the ice was melting. This is one in Glacier Bay. It's probably about 10 miles long and coming down thousands and thousands of feet from a mountaintop, and it is moving quickly. There are basketball-sized boulders coming out of it, but a huge quantity of mud, which you can see on the lower right. Well, we had those things happen here too. On the upper right, you can see some of the mud deposits that blanketed our landscape formed precisely the same way as those in Alaska. The old map from George Stone in 1893 on the left shows the approximate extent of these, the low areas heading up many of our major river valleys. On the right, you can see the extent of that glacial marine mud and the extent of the areas that were covered by the ocean. Our coastline was very, very different then. Ocean water even came down the Gulf of St. Lawrence and turned the Champlain Sea into an ocean body. And I usually ask my class when I show this, does anybody know the name of the state fossil of Vermont? The last time I taught that course, someone knew it, and no one had ever known that in 25 years, but it's a whale, and it was dug by a farmer on the shores of Lake Champlain. He had no idea what it was doing there. Since it's a freshwater lake today, he assumed Noah's flood had allowed it to be there. On the left side, you see what a map might have looked like in our area where I am, at least in the Orono region. You know, hills sticking up that would have been islands, but a very different coast, and one which changed constantly because the land, after the ice was gone, began to rebound vertically upward. This is as far landward as the land got, and it's one of the many features like this. This is Pineo Ridge. It's a LiDAR image showing us kind of what it looks like in topography. The glacier sat on the backside there in what is now the Great Heath, and it poured out huge amounts of water and sand and gravel across this deltaic feature. You can see the channels, but the land began to uplift even as the glacier was melting back. And you can see the channels as it left and the gullies that it started to cut into. There are shorelines etched along the face of that. You can see one here marking the highest point of sea level and then the fairly rapid retreat of the ocean as the land emerged. These are just some of the components of a delta and the way we determine when it formed. You can see the top, the river deposits, the topset beds, and then an abrupt shoreline where the ocean, in this instance, a puddle in a gravel pit, met it, and then the foreset beds, the steeply dipping beds where material just dumps into the ocean. And you can see various erosional features along the side. Well, we have those everywhere in Maine, and these have been thoroughly looked at. These are deltas that you see here. They're blueberry barrens today, but each one of them, if you cut them open, looks like this. The topset beds at the top, and the contact between the topset and foreset beds marking the location of sea level, and the lucky person is the one who finds a fossil shell there that can be radiocarbon dated to tell us when sea level was at that location. There are other features, sea stacks. You can see a modern one in Acadia National Park with a sea cliff, Boulder Beach, a sea stack. And then you can see a paleo one, not more than a mile away and 220 feet higher, marking the highest stand of the sea. It also has a cliff, a sea stack, and a boulder beach. I won't go into this too deeply. This is a long graph, but if you look at the graph on the left, 0 on the axis you see there in elevation is sea level, and 0 on the bottom axis is today, 0. If you go back 15,000 years ago, you can see when those deltas were forming, and some of the dates we've gotten from those. But sea level fell rapidly at first to a low point about 60 meters below present because the land uplifted. After that, the ocean really took over and began rising rapidly, then slowly, then rapidly again, for reasons that take quite a bit of time to discuss. But you can see a number of the points we've radiocarbon dated. Each one of those cost $500 to date, and let's just say there's millions of dollars to produce that. One result, though, you can see on the right is a delta, and it's the delta of the Kennebec River, but not modern, the ancient delta. The yellow and green rather, sand and gravel, and they represented a time when sea level was at about 60 meters below present. Well, to find out when that was, I went out on a boat with coring equipment and colleagues, and you can see that 6-meter piece of pipe they're pushing off the boat. We lowered that down. It has a vibrating head at the top, and it sank into that sediment in about 30 or 40 seconds. And we pulled up a large core of it so we could see the record, hoping we could date the topset foreset contact. Well, we found some wood fragments, which they could have died a long time ago, and some shells, but they weren't in place. But that's the extent of it. It's a very difficult thing to do, and that's sort of where we are. I spent most of my life working offshore, and I can't help but show some pictures from that. What you see here is not what most people think the coast of Maine is like, but the green areas are natural gas fields. They're methane deposits. It means that more than 5% of the space in the sediment are bubbles of methane. Natural gas that you could use in your house. There's not enough of it to make this an economic deposit, but it's a definite hazard. As you can see in the places in right, these are the gas escape pockmarks. Here you see Belfast Bay up in Penobscot Bay, but you could find this sort of thing many other places. Thousands of craters in the seabed, in the shallow seabed. I mean, the seabed there is about 20, 30 meters deep, and then there are these holes. The deepest is about 35 meters deep and about 400 meters in diameter. That's the size of the Rose Bowl with the stands. Any house you see along the side of the road would disappear into one of these holes in a moment. These are truly gigantic features. Again, I could talk a lot about this. I love the drawing the Portland Press Herald did when we went down on some submersible dives. But if you go down and look at them, you can see material venting. Most of what you see there is mud, but there is methane pressurized that's driving it, and as well as some salt water. Interesting features. There's so much more to learn about them, but you don't want to put your utility line across one of these fields, or you'll come to regret it quickly. How did they form? Well, in a quick cartoon here, I think they were lakes when sea level was lower, and lakes generate a lot of organic matter. The ocean came up, sediment covered that organic matter, and now bacteria are breaking down the organic matter, making methane, and it pressurizes up and then blows its way to the surface. One hypothesis, the published hypothesis. One other thing I couldn't help mention is Bass Harbor. You can see the stone point on the upper right. A scallop dragger brought that up, and it looked like a great idea. Stephen Clayson came to see me, and we decided we'd work on this as a proposal to see what might be there. So we went down, and this is the area, that black dot that says BH-03 is approximately where the scallop dragger was working. You can see that dashed white line, something called seismic reflection. I sent sound down, and it reflects off layers from the seafloor and many of the layers beneath it. And the red arrows point to shorelines. They were areas that were temporarily beaches. You can see where that core is. I drilled into that because that's a beach. Those are two little spits that form from the erosion of the glacial materials. And you see part of the core on the right, and it had a lot of mud when it was somewhat sheltered. And it was full of eelgrass, just as green. It was starting to turn brown here, but it was as green as eelgrass you'd see growing today. Lots of things to date here, from oysters and mussels and clams. So we've got a really good chronology of when sea level was at about this point. And we got a good idea how this formed. You can see it today in a multi-beam bathymetric image. Here you can see the dotted line and many of the shorelines that were probably pretty temporary, but people were no doubt living here. Here are the eroded glacial deposits. The beaches that form from them are in yellow, and the river coming in, the tidal inlet. It's all there today, but underwater, and possibly there's an archaeological site located on one of those sandy beaches. I flew over the area just looking around, and I couldn't help but notice this is a perfect analog. It's less than a mile away. There's your little beach. This is what that area that's underwater now, it's about 120 feet of water, would have looked like. The dark area in the water are mussel and eelgrass beds, clams, no doubt to be found in the region, some eroding glacial deposits, really a perfect analog. Modern processes, storms. Storms are the major players here. Summer waves are great. They bring sand to our beaches, but the winter waves bring storms much closer to shore and can cause considerable damage to the shore and to properties. I could show these kind of pictures all day. It's a very sad thing. But it's an important process, and here it is with no houses, and we can see what happens when a storm hits Sand Beach in Acadian National Park. Overwash or wash over occurs, where sand is moved from the ocean side of the beach, washed across into the dunes initially, but in a bigger storm through the dunes and onto the bay side. And in the process, the beach changes its location. We might say it erodes, but that's not really appropriate. The same volume of beaches there is just got a new address. It's moved more landward, and it's a little bit higher than it was. So it's moving away from the rising level of the ocean. It's an image of a natural beach showing how things change over time. I looked at the Google Earth 2003 image on the upper left, and I traced that red line mapping the border between the overwashed sand and the salt marsh. And I dropped it on top of the 2010 image. You can see that the sand has already begun to move well landward of the 2003 at a rate of about 6.5 meters per year. The middle image is just an oblique photo I took in 2012. And the lower right is the 2018 image. And you can see that the sand is continuing to move, to be driven landward as sea level rises and this beach is moving landward. It's moving into that tidal creek. This is no small matter. Once it intersects that creek, tides are going to start to want to come in and out of there, and we're going to probably start to form a tidal inlet, which could completely change the geology, the geometry of this part of the coast. Fortunately, it's undeveloped, but there are places where this could happen on developed properties. Getting toward the end here, it's a sad observation, but this is the nature of our coast. You see the park area near Biddeford Pool, town of Biddeford, out on Fletcher Neck. It has actually moved back from the edge of where the seawall was to its present location since the 1980s. And it actually has a sheet metal seawall protecting the bathhouse there. But notice the red dashed line. That's where the shoreline would be on this beach if that seawall didn't exist. I'm not advocating seawalls by any stretch of the imagination. In fact, if the seawall weren't there, there'd be more sand to share. But still, these houses are out of equilibrium. This is not a safe place to really want to be. So I'll wind up with this and say, well, this is what our coast looks like. It's very developed, except where there isn't any development. That's generally a park or something perhaps the Nature Conservancy owns. But where it's developed, it's very developed, and it's very not sustainable. Sea level is going to rise. It's likely to accelerate. It is accelerating its rate of rise, and it's likely to, storms will come and pick off individual houses over time. More and more money will be spent. But the bottom line is these people are really on their own. The state doesn't have the kind of money it would take to protect this beach by adding large volumes of sand. They get about 100,000 or so yards of sand added every time they dredge the inlet. But that's only once every 10 years, and it doesn't last. These are going to be problems facing voters and facing politicians in years to come. With that, I can end, and I don't know who takes over next.
No, I take over. So if you will just stop the screen share, I'll take it from there.
Are we set?
We are set.
So much, Joe. I am officially ready to sign up for your full semester-long course because wow, that's incredible. I can't wait to get into some of the great questions that have been coming in, and if you haven't sent those through the chat, go ahead and do it now. As many of you know, this is the part of the program where we share a call to action. And today we are focused on helping each other make a plan to vote in the November 3rd election. And we have a poll to help personalize those calls to action today. So I'm going to launch that right now. Have you requested your absentee ballot? Are you making that request today? Let us know. And while you respond to that, I'll share a little bit about MCA's voting plan. We are working to ensure that all Maine people can vote safely this election season. And that's an important phrase because it really is an election season this year. We're looking for volunteers to help increase absentee voting. The really fantastic thing about absentee voting is it helps make sure that in-person voting is safe and efficient for people who really need it. We're going to kick off that campaign this coming Tuesday, September 15th, and I am now going to drop a link in the chat. Here we go. So if you click on that link, you can sign up for our event this Tuesday from 6 to 7 p.m. And we'll share some more opportunities for you to get involved in absentee voting. So let's see. Here are our results. Oh my goodness, congratulations. We've got 80% of us on this call have already requested our absentee ballots. Way to go. Make sure to mail those back with plenty of time. The post office is recommending at least 2 weeks, which doesn't seem right to us, but is important to know what that timeline is. And thanks for everyone participating in the poll. Let's get to some questions. All righty, what have we got? Dr. Kelley, your comment about the methane deposits along Maine's coast had raised some flags for some of our participants. Are we at risk of coastal energy development because of that?
Good question, and I didn't have time to go into it, but the answer very simply is not a chance. When you see oil and gas produced down in Louisiana or someplace, it's coming from 30,000 feet down, enormous confining pressure. So it doesn't take a big volume to have a lot of gas in it. Ours is 10 meters down. It's just not in the same ballpark, and it never will be. So no, not to be concerned with that.
Thank you. You also mentioned the economic impacts of rising sea levels and the sort of, I know seawalls are a possibility there. Is there anything more you want to say about those from a geology standpoint?
Well, seawalls destroy beaches but protect property, and they should be looked at that way. There are certainly some infrastructure on our coast that we have to protect, critical roads and facilities. We passed a law in Maine. Well, I wasn't actually in Maine at the time. I was in graduate school, but after the 1978 storm that said it was unreasonable to interfere with the natural storage and movement of sand on the coast. That clearly meant not to build seawalls, but it didn't say that. I was actually hired, and along with some people from Maine Audubon Society, we developed some rules that then later became codified as laws and under the Natural Resource Protection Act that says you can't build a seawall. So that doesn't mean you couldn't, it means you would have to get the legislature to come together and say, yeah, you can build this seawall. Something that's not very easy to do, actually. So it is an option. It's the first thing people think about. Oh, my property's eroding, I better shore it up with some rocks. But you're going to see the beach disappear. And that picture I showed of Biddeford Pool, let's just say at high tide, there's no beach. The day's going to come when children, say to their parents in Wells or any number of places, why is this called Wells Beach? There's no beach. Because at high tide, there isn't today, and increasingly it's going to be at most stages of tide. Go to places in Europe or places that have been developed for hundreds of years and had seawalls. There's no beach. It's just, the ocean has to move landward if sea level's rising for us to maintain our beaches.
Thank you. We have another question about that. Are building codes an option to help prevent some of that development? You noted that we have either completely undeveloped coastline or, from a geological perspective, overdeveloped coastline.
Yeah, the law is very clear. You can't build in the frontal sand dune. You can't build in front of a sand dune. You'd need a permit, and you would not be given a permit. So it isn't locally. This is enforced. This is a statewide sort of thing. Other sorts of structures, I didn't get into other ones, but jetties and breakwaters are also strictly banned. They all obviously interfere with the movement of sand, that may be a route that some people try to move us toward in the future. We face a very difficult situation with, I mean, I don't know the economic value of all those houses at risk on the coast, but it's very large and it's very personal to a lot of them. To say casually, oh, well, the big storm's going to take them out, that's crazy. I mean, these people are not going to go away, and they, you know, they have real investments there. So we're going to have to come up with a social contract that deals with this. I mean, I won't go into names and places, but I've known beaches where the town said, listen, we'll give you land nearby if you'll move your house. They wouldn't contemplate it, even though they face the risk of complete loss of their property from the next storm. The thought of moving was just out of the question. And so we wait for big storms to move properties. Unfortunately, it's not a good way to do it, but that's the way we do it.
Yeah. Well, I'll put a little side plug in here for some of these very issues are being contemplated by the Climate Council right now. So it's a good moment for us to all be thinking about our coast in a different way. We had a question about how unique Maine's coast is, and particularly, how does the Katahdin granite outflow compare to something like Yellowstone or the Deccan Traps?
Perfectly great question. In fact, in the paper, Sheila Siemens compared Katahdin to Yellowstone, and Yellowstone was not nearly the size of Katahdin. Which is really big because that's one of the largest eruptions. Yellowstone's one of the largest eruptions we know of in the last million years. But really, she steps back and goes, there may be a few places on Earth in the last few hundreds of millions of years that are equivalent, but not many, and we certainly don't know about many of them. The Deccan traps are very different. It's a great question, and the Siberian traps would be similar. They are like the black basaltic rock that I showed with the beginning of the Atlantic Ocean, and trap rocks like that can indicate the beginning of formation of an ocean. That may be what's happening in India, and that may be what is slowly happening in Siberia, but they're very different sorts of rocks.
All right, and here's another question about the Katahdin granite outflow, and I'm going to be completely honest with you. I understand very few of the words in this question, so.
A technical one.
Was this a short cataclysmic volcanism with high viscosity, high in feldspar and quartz, or more the high temperature form that later had quartz inclusions develop? I trust that means a lot more to you than it does to me.
Well, it's not my specialty, but I do know what it means. These were silica-rich, aluminum silica-rich volcanoes. That's sticky stuff. It really plugs, so you form volcano shapes, and they get jammed. And typically what happens, granite, when it's liquid and comes out, we give it a different name, but when it's molten, it's about 600-700 degrees. And then it gets sometimes, and it did get injected by basalt, the dark black rock. That's much hotter. That's 1200 degrees. When that hot stuff hits the granite, it just blows the top off. Think Mount St. Helens. Before that, it was Mount Lassen in California. Suddenly, the pressure goes crazy and we blow up the volcano. And that's what certainly happened to the volcanoes along our coast. The black basaltic stuff that I showed, just the tabular sheets coming up, would have been like the Deccan traps, and it's so hot it just flows like water. So you can't form a volcanic shape. It just pours over the landscape. Think of some of the volcanoes. Well, I actually can't think of one that's been active lately. They don't usually show it. Iceland has volcanoes, not volcanoes, but eruptions like this, where cracks open up and lava just pours out. That's what these were like.
See, you are such a good teacher, because now I know what we're talking about. Thank you.
Okay.
And as a reminder that geology is something that we can all explore, we've got a question about, what is your favorite area of the state to explore from a geologic perspective?
That's a hard question. And other friends of mine have heard me say this, but when I go on vacation, I'm actually going to rent a camp for a week next week. I go to the mountains. I love the coast, but this work, that's my office. I don't go to the office for fun. So I prefer to go to the mountains. I really like Baxter Park, and I've crossed it in the wintertime on skis more than a dozen times with friends. Love to go up there in summer or winter. In terms of the coast, I like the undeveloped coast because I like to see beaches in a natural state. Jasper Beach is certainly a favorite down in Machiasport, Maine. Lubec, the easternmost beach in the United States, spectacular area. So some favorites.
You can't really go wrong here, can you?
Yeah.
A question about the sand migration. You talked about beaches moving, which we can see happening. Is there any migration of sand that's going into the deeper marine environment?
That is a $1,000 million question. The answer is certainly yes, some. If you go seaward of, let's say, Old Orchard Beach, seaward of the pier, and I have some great illustrations of what it looks like. Old Orchard Beach, all of Saco Bay there is about 30 feet thick of sand before you get to an Ice Age mud deposit. And it tapers like a wedge to about 5 inches thick, probably a couple of miles offshore. Some of that sand will be left behind. As Old Orchard Beach tries to move landward, there'll always be that little bit of sand spread across the seabed. Not a thick deposit, but some, and so some is left there. Really operative question is that when a big storm comes, if it can't wash across the beach, across the dunes and into the bay, the waves reflect off a seawall, that sand is washed out to sea. So when you look at a beach at high tide with no sand on it, like parts of Wells Beach, parts of it, not all of it, there is sand that has just been driven away. It can't stay between that high energy wave coming in and then reflecting off the wall and going back. So yes, we can, particularly around developed properties, we can see loss of sand to the offshore and permanent loss of sand to the offshore. Just to add to that, the Saco River mouth, the Kennebec River mouth, both these rivers deliver sand annually to the ocean in the springtime. Actually, I had a research project on that. I lost a bet because I didn't think that happened, but it does, and we showed that it did. So they add a significant amount of sand to those areas of the coast, but not in Penobscot Bay, not in other places. Those are the only two places we're actively bringing in significant amounts of sand every year.
What are the fastest changing parts of the state from a geologic perspective?
The fastest changing, I really didn't talk much about. I showed one picture. The beaches change, but they move landward, or they do what they do. But we understand that, and that's okay. It's bluffs. It's these cliff-like bluffs of loose ice age material. And there's no real strength. I had a homeowner once living on a bluff made of mud, nothing but mud, who was upset that they just lost a lot of their property to a landslide. And and this person was a retired high school science teacher. I said, well, so what do you think you built your house on? And they said, well, the rock-bound coast of Maine. And it's mud. This mud is not rock. It's mud. It has no strength. It's those bluffs that are most susceptible to erosion, and they line the inner part of much of our coastline. It looks like lucrative areas to develop, although in fact it's the last areas that have been developed because people, had some good sense and said, no, that looks risky. It's straight down and there's no vegetation supporting it. It's telling you something. Those are the areas subject to change. Oftentimes when a landslide does happen, it delivers, large volume, 500 truckloads of mud essentially to the coast, which protects it for some time. And it's unfortunate to the homeowner not knowing this, who walks in and go, oh, this looks stable. It's all vegetated and there's that nice little pile of debris out there that's eroding. Yeah, because the waves will wash through that landslide deposit eventually and then get back to where it was on your property. So it's the bluffs that are really the most dangerous, and they're really the part that people don't understand. Beaches, we hear about beaches. Other states don't have bluffs like ours. And so I don't say Maine's unique. Washington State does, Alaska does, but other states don't have these mud deposits the way we do.
And where was that last slide, the one with the stretch of homes close together on a spit of land?
The last one was Wells Beach.
Wells Beach, okay.
Looking from I rented one of those condominiums. It was work, running one to do some work one summer with a bunch of students. And I was off season, and it was taken by the view of looking over buildings, over marsh. There's one natural area in the middle, and it's clearly getting squeezed out by the rising water in our buildings.
All right, so if we zoom out, what does Maine's coast look like in 100 years or 1,000 years?
Oh, gee. Let's
Where's
stick
your
with
crystal ball?
100 is a lot easier. Thousands.
Okay, we can start there.
100 years, sea level will rise a great deal, more than a meter. I mean, far more than it has in the last 100 years. It will, a lot of wetlands that are freshwater wetlands will be intersected by this and will become salt marshes, and that's not a bad thing. That's pretty good. Areas where people live adjacent to marshes and they built maybe a small wall to keep the water back, well, you're going to have to build high, I think a meter, and then there's storms that come on top of that, so you want to meter even higher than that, and that it could be much more than a meter. It could be 2 meters. That's 6 feet. So our coastline is going to change. It's going to be very painful. Hard to say where. Beaches, if you just take in a computer and drop water and say, all right, it's 6 feet higher than it is today, it covers beaches, but that's not fair because beaches have ways of moving landward and reorganizing their sand, so they don't drown passively. Salt marshes are also always shown as areas that will drown, but they don't drown passively. They actively add mud every year, and they can hold their own. Not to really rapid sea level rise, but to some, and areas that erode will contribute their eroded remains to the remainder. But we're likely to see changes in what we call the soft coast. The bluffs will retreat. It's really hard to stop that. The beaches will change their orientations, perhaps, will change their volumes. There won't be so many people on them. And the salt marshes will move landward. So it's going to be a different coastline, but not radically, step back from, space or something. It won't look too different. And where erosion does occur, bedrock will start to emerge, and it will just become somewhat rockier. And where we live and try to hold it, it will become very rocky because there's really no way to hold it back, short of pouring sand in front of it, which, as people find out when they do it, is a very, very expensive proposition. So it's going to look different, but it looked different 1,000 years ago or 500 years ago, and we like the way it changed. We would like the way it would change, except we've invested heavily without knowing anything that I've told you in the present location of the shoreline. And prices go up as you near that very dangerous place. And so it's going to be painful for some time for many people, for all of us, really.
We talk a lot about the sea level rise. Do changes in the temperature of the water have an impact if we were to isolate those from the sea level?
There's two things that affect contemporary sea level rise. They're about equal, more or less. One is warming the water, which expands it, and we see that expansion as a rise in sea level on our coastline. And the other is, of course, melting glaciers that are on land. If it's on land, then that water from the melting ice is going into the ocean, adding volume there. There was a silly movie years ago, I can't remember its name, but begin with a scene showing the Arctic ice melting and seas flooding New York. No, the Arctic ice is floating, and it is melting, and that's sad, but that's not going to flood anything. It's ice that's on land that's melting. So those are the two things that give us our sea level rise. But to say, in a lecture on this, there are 9 factors that I go into, not the least of which are those involving the land. The land isn't changing here. We're not fixed on land. Land in Maine, if you go to the west, is rising slightly. And on the coast, it's right on the edge of rise and fall, pretty much neutral. If you go out just a little bit seaward of us to Nova Scotia or Cape Cod, the land is sinking, and therefore relative sea levels rising rapidly. When the ice came down and pressed on our landscape, it squeezed material below well south of of where the glaciers were, down to Maryland and places like that. Well, the reason the land is coming up here, coming up in Hudson Bay, is that that material squeezed down below is coming home. Sad for, I mean, it's nice for us, but it's sad for them because they are sinking rapidly and sea levels rising on top of it. I mean, there's compaction issues in many places, not here, luckily for us, but you know, the Gulf Coast, the Barrier Islands, where they pump water from the ground for their drinking water, well, it's sinking, and the ground is sinking rapidly, you know, over an inch a year in some parts of Louisiana. It's just, and then sea levels rising on top of that. So there are other factors that affect what we think of as sea level rise. We call it relative sea level rise, meaning it's just land relative to the sea, and it's difficult to separate them one from another because the impact is on a tide gauge, perhaps the sea level has risen. And identifying exactly how much comes from one place or another, and people try to do it, and there are papers on it, is a difficult thing to do.
What are you working on right now? What's up on your research agenda?
Retirement? No, I am retired, but no, I have a grant. In fact, I'm glad you mentioned it, to scan my slide collection of the Maine Coast and put it on a searchable database at the Maine Geological Survey, a state agency. I'm 4,400 slides into it so far. I've got a student now again who can help me scan them, and they will be free. They'll be available. All the slides I showed just now certainly would all be available. And should be sometime this fall, maybe November. We hope, our goal is 8,000 slides. So whether we get quite to there or not, I'm not sure. They'll just be Maine, but it was a grant from the U.S. Geological Survey called Data Salvage, you know, to save. As a faculty member, I was ahead of my department. I remember going into offices, they left, they retired, and they're gone. And there are these thousands of beautiful color slides, but they're not labeled. I had to throw them all away. I don't know what to do with them. So I thought, well, I'm not going to let my heirs throw all these slides away. I'm going to identify them, label them, and put them out. And so that. I have a grant to work in South America, a National Science Foundation grant. We didn't go this summer, but we went last year, and hopefully by this summer of next year, we'll be able to go back. We're looking at how coastal processes have changed in an area with some ancient archaeological settlements on the southern Peru coast. I'm finishing a book called The Rise and Fall of the Maine Coast, and I'm on the last part. I decided to add a kind of a denouement, a last chapter to wrap it up, and that's what I decided I need to finish, and that hopefully will be coming out by next summer. So there's plenty of things to stay busy with. I got a new puppy. You want to be busy? My wife is outside walking the puppy right now, so I could talk with you.
That's fantastic, and I can't wait to see all of those slides and to read the book. And if we want to explore the Maine coast ourselves, as we all do, right? We know that. What should we keep an eye out for? What should we be looking for when we go out and explore this incredible state?
Well, I've often said, I've said to every one of my students, you know, every coastal photograph you take is a before, because it's going to change. Maybe people build a house there, or a storm will take a house away, or the beach it'll just change, except the rocky cliffs. You know, I've looked at pictures of Portland Headlight from the 1800s and, you know, just today, and it's just not changing. Our rocks don't erode. Not to be concerned with our rocks. If you're on a rocky cliff, you're probably all set, but everything else is changing. So I like to see dynamics when I go. I like to look at things that are going to change in the future, perhaps have changed since the last time I visited. And that's why I tend to go to more natural places. They change more rapidly, although, you know, even in developed areas, change occurs. And I've been scanning these slides going back to 1982, and it's really shocking. I didn't even notice changes happening, because you see them. What's the analogy is, you put a frog in some water and heat it slowly, he won't jump out, but if you put a frog in hot water, he'll jump right out. Well, we're all just sitting there letting the water get hot, watching change happen slowly and not really seeing it. It takes images to remind us that, oh, it was different once before, or maps. You know, lots of islands on the coast of Maine have literally disappeared, particularly in southern Maine, but all over the coast. So I look for things that change because there's beauty to change, I think.
Well, I can't in good conscience keep us from getting out there and exploring it ourselves, because it's a beautiful day, and you shared such such incredible information and inspiration about how we look at the world around us. Thank you so much. Thanks to everybody for joining us today. We will email you a brief survey later this afternoon, and that feedback is really helpful. So thanks for taking a few moments to fill it out. If you enjoyed our conversation today, I encourage you to meet us back here every Friday at noon. These lunch and learns started as a bit of a lark back in April when we were looking for ways to stay connected with each other, and have rapidly become one of my favorite parts of the week. So thank you for joining us. Next week, Hannah Pingree, Director of the Governor's Office of Policy, Innovation, and the Future, will join us to give an update on the Maine Climate Council's work to develop a new climate action plan. That plan is due to the legislature on December 1st, so the council is heading into the home stretch, and this is a great time to check in. Thank you again, Dr. Kelley. Thank you all of us for joining us. Have a fantastic weekend, and go explore some changes in progress.
There you go. Thank you.